Here's a quick recap of Chapter 3. We started with parallel lines and planes, and we defined parallel lines as being coplanar lines that don't intersect. Then we said that segments or rays, they can also be parallel, or they can be skew. What are skew lines? They are non-coplanar, and they don't intersect. So they're not parallel because they're not in the same plane. Then we talked about parallel planes. If two planes don't intersect, they are parallel. Two planes are going along and they're parallel, and then a third plane comes by and intersects those two, then the two lines of intersection are parallel. Okay, then we started talking about this transversal thing. Transversal is a line that intersects two or more coplanar lines, and when that happens, you get all these angles. You get alternate interior angles. That's in blue. Those 3 and 6, those are alternate interior angles. 4 and 5, those are non-adjacent interior angles on opposite sides of the transversal. Then you got the same side interior angles, so they're on the interior of the two lines that are being intersected by the transversal, and they're on the same side. Then corresponding angles. That means they are in corresponding position relative to the two lines. So in this example, 1 and 5 are corresponding, 2 and 6, 3 and 7, 4 and 8. Okay, we went on to properties of parallel lines. Now all those things with the two lines and the transversal, they took on kind of a new meaning. When those two lines are parallel, then corresponding angles are congruent, and alternate interior angles are congruent, and same side interior angles are supplementary. And then if you've got one perpendicular line, then the other is perpendicular. Kind of the same thing as corresponding. Okay, so we went on. We started proving that lines were parallel. Kind of the same thing as the last section, except the converse. Now, if we can show that the two corresponding angles are congruent, then the lines are parallel. Or if alternate interior angles are congruent, then the lines are parallel. Or if same side interior angles are supplementary, then the lines are parallel. And finally, if two lines are perpendicular, then the lines are parallel. There's a couple more theorems that went along with that. Through a point outside of a line, there is exactly one line that's parallel. That's the blue line. And then there is exactly one line that is perpendicular. Again, the blue line. Finally, if you have two lines parallel to a third line, then those two lines are parallel to each other. So in this case, if C is parallel to A and B is parallel to A, then C is parallel to B. We went on to the next section. We started talking about triangles. And you've got scaling triangles, isosceles triangles, equilateral triangles, depending on what the sides are doing. Then you've got acute triangles, obtuse triangles, right triangles, and equiangular triangles. Again, depending on what the angles are doing. The first theorem we looked at was the one about the sum of all the angles in a triangle. And we found out that it's 180. It's always going to be 180, 180 degrees for those three angles inside of a triangle. So some corollaries went along with that. If you know that two angles of one triangle are congruent to two angles of another triangle, well, that means the third one has to be congruent to the other one. And then we found out there can only be one right angle in a triangle, or obtuse. And in a right triangle, the other two angles, in this case angles 1 and 2, those are complementary. Because we knew that all the angles add up to 180. One of them's 90, so the other two must add up to 90. And three angles that are the same, that add up to 90, well, guess what? They're 60 degrees. In an equiangular triangle, 60 degrees. Then we started looking at this exterior angle. In this case, it's the angle 1 in red, and then how that relates to the remote interior angles, in this case 3 and 4. Well, as a matter of fact, they're the same. The measure of angle 1 equals the measure of angle 3 plus 4. So 1 is the sum of the remote interior angles. the exterior angle is the sum of the two remote interior angles. Alright, we got to polygons finally. In 3.5 we looked at convex polygons where there's no point inside, and then non-convex where you've got a point on the inside. If you wrapped a rubber band around that non-convex, it would not hit all the sides. Mostly we talked about convex polygons though. We drew a diagonal in. That a diagonal goes from one vertex to another, one corner to another. And look what happens when you draw in all of the diagonals that you can from one corner. You make a bunch of triangles. Well, as it turns out, you make 2 less triangles than the number of sides. So this theorem showed up. The sum of the measures of the angles of a polygon with n sides is n minus 2 times 180. Because there's really, like in a 6-sided triangle, there are 4 triangles in there. So you take the number of sides, subtract 2, and multiply it by 180. When you're looking at the exterior angles, no matter what, I tried here with a square and a triangle and a hexagon, and it always worked out to be 360 degrees when you add up the exterior angles. And when we talk about regular polygons, that means all of the sides and angles are congruent. If they're not regular, we can't say that their sides are congruent. And that is it for sections 3.1 through 3.5. 3.6, we'll look at indirect proofs, and we'll talk about that in class.